Hello everyone. In previous section, we discussed about most common reactions of alkenes. All those reactions fall under the general category of electrophilic addition reactions. Apart from electrophilic addition reactions, alkenes also undergo oxidation and reduction reactions. This section deals with all the redox reactions shown by alkenes. We will begin this section with a review of definitions of oxidation and reduction. As you may recall, oxidation is a process in which a loss of electrons take place, and reduction is a process in which electrons are gained. Now, in organic reactions, it's hard to visualize loss or gain of electrons. Uh, Therefore, we use an alternative definition of oxidation and reduction, which deals with loss or gain of hydrogen and oxygen atoms. According to this alternative definition, any reaction in which loss of hydrogen or gain of oxygen or both takes place, that reaction is oxidation. And similarly, any reaction in which hydrogen atoms are gained or oxygen atoms are lost, or both of these processes may take place, that reaction is known as reduction. So for example, if we start with an alkene, let's take an example of propene, and it reacts with some reagent. Let's call this reagent X. We will discuss what is this X reagent in a little while later. So just for now, just imagine that it reacts with some mystery reagent X, and after the reaction, alkene changes into alcohol. In fact, it will change into a diol. So diol is the alcohol in which we have two OH groups. Now you can see that in this reaction we have gained two oxygens. So therefore this reaction is a oxidation reaction, because any reaction in which uh, oxygens are gained is a oxidation reaction. Now similarly, let's imagine that we start with the same alkene, propene, and then some another mystery reagent Y. We will talk about these reagents in a few slides later, but for now just imagine that alkene reacts with a reagent Y, and the end product is a alkane. Okay. So now in this case, you can see that we have gained hydrogen, and the gain of hydrogen is a reduction. So this is an example of reduction reaction. Also remember that in order to balance redox equations, we use half reaction method. So in this, we write the half reaction showing one reactant and its product, and then we complete the material balance, and we use water and H positive in acidic solution to balance the half reaction, and then we use water and hydroxide ion in basic solution to balance the material, and then we balance the charge using electrons, and after two individual half reactions are balanced, we add them up to balance or to get the completely balanced redox equation. The method of balancing the half reactions is same what we learned in previous course of general chemistry. The oxidation reaction which I wrote in previous slide, after balancing, you can see that this reaction also involves loss of electrons, so hence this is a oxidation process. Similarly, if we balance the reduction reaction which I wrote in previous slide, you will see that that reaction involves a gain of electrons. So our alkene is gaining the electron to go from alkene to alkane. So hence this reaction is a reduction reaction. And these two equations are balanced half equations of oxidation and reduction process. Some transition metal oxides, such as oxide of osmium or manganese, are effective oxidizing agents, and these transition metal oxides will oxidize alkenes into 1,2-diols. Now 1,2-diols are those compounds which contain two hydroxyl groups present on adjacent carbon atoms. For example, if we start with an alkene such as propene and we treat it with oxide of osmium or osmium tetroxide in this case, there are some other reagents also which we'll discuss in a little while. The end product will be a compound in which two hydroxyl groups are present on adjacent carbons. So this is known as a diol or 1,2-diol. Now 1,2-diols are also known as vicinal diols, or they are also known as glycols. Osmium tetroxide is highly electrophilic, and it adds to alkenes in a single step. This addition has a syn stereoselectivity. Syn stereoselectivity means that the hydroxide groups will add on the same side of the sigma bond structure. Apart from the metal oxide, the reaction also needs sodium hydrogen sulfide and water. So because of the syn stereoselectivity, if we use osmium tetroxide to oxidize a cyclic alkene such as cyclopentene shown here, we will only get a cis glycol because both alcohol groups are added on the same side. The syn stereoselectivity can be attributed to the formation of a cyclic intermediate, and this cyclic intermediate is known as cyclic osmate. Now, in order to form this cyclic intermediate, both oxygens has to be on the same side. So therefore, the end product is the syn addition product. Therefore, we can say that this 5-membered cyclic osmate intermediate is responsible for maintaining or retaining the syn stereoselectivity of this reaction. Cyclic osmate intermediates are relatively stable intermediates, and they can be isolated and analyzed. And usually cyclic osmate intermediate is treated with sodium hydrogen sulfide in presence of water to cleave the 5-membered ring structure into a glycol. It should be noted that osmium tetroxide is both extremely expensive and highly toxic. Therefore, it is used in catalytic amounts, and it is used in presence of other oxidizing agent to reoxidize to its reduced form and thus recycle osmium tetroxide. So two commonly used oxidizing agents are hydrogen peroxide and tertiary butyl hydroperoxide. So these oxidizing agents will react with the leftover part of osmium oxide after the cyclic osmate step, and they will reconvert it back into osmium tetroxide so that it can be used to do the same reaction all over again. All the reactions which we have seen so far in this chapter involve cleavage of a pi bond, and an atom or a group of atoms will add across the carbon-carbon double bond. However, oxidation with ozone is one of the reactions in which the carbon-carbon double bond is completely cleaved. So therefore, this is also known as oxidative cleavage of alkenes. So carbon-carbon double bond completely broken down, and something, well, in this case is oxygen, is added on both sides of the carbon-carbon double bond. So this kind of a reaction is known as oxidative cleavage of alkenes. So treatment of any alkene with ozone followed by a weak reducing agent will cleave the carbon-carbon double bond and forms two carbonyl groups in its place. Uh, in this example, the weak reducing agent is dimethyl sulfide. So if we take a look at this example, in first part of the reaction, ozone will cleave the double bond. So this double bond will completely break off. So this section, I'm going to write it here. Okay. And the remaining section, let me write it here, after the cleavage. And instead of the carbon-carbon double bond, the ozone adds oxygen, hence it gave rise to carbonyl group. So as we can see that the carbon-carbon double bond has changed into carbonyl groups. This is a ketone and this molecule is an aldehyde. This is one easy way to understand what products will be obtained when um, uh, an alkene is cleaved with ozone. Let's analyze the mechanism of ozonolysis of alkenes. In this reaction, ozones will react with alkene to produce an initial primary ozonoid, and this initial ozonoid is also known as mole ozonoid. So let's take an example of an alkene. It's a branched alkene, and let's react it with ozone. So in the first step, this is our ozone. Alkene, as we know, is a nucleophile, so it will attack the electrophilic site which will trigger a formation of a five-membered ring intermediate, and this five-membered ring intermediate is known as initial ozonoid. This is our initial ozonoid, or it's also known as mole ozonoid. Now, relocation of valence electrons in mole ozonoid will result in the cleavage of this carbon-carbon bond and one of the oxygen-oxygen bond. and two fragments will result. So let's take a look at what those fragments are. So these fragments relocate in this manner. uh, and we get two fragments, and if you notice that carbon carbon double bond will cleave at this point. So our mole ozonide relocates its valence electron, and we get two fragments as shown here. Now these two fragments then recombine with each other to form a five-membered ring structure called ozonoid. Initially we got mole ozonide, now it's gonna recombine to form ozonoid. You should be very careful to show the head of the curved arrow and the tail of the curved arrow. So for example, our curved arrow here is representing that the lone pair of electron is attacking the carbon or making a bond with the carbon, whereas this curved arrow is showing that the pi electron is making a bond with this carbon. So we should be very careful how we are describing our curved arrows, and this curved arrow is showing that the pi electron from the carbon-carbon double bond is moving to oxygen. So after this rearrangement, we will get a ozonoid. So ozonoid is a five-membered ring structure. So this is our ozonoid. So when ozonoid is treated with a mild reducing agent, so in this case we are using uh, dimethyl sulfide, but other mild reducing agent will also work. So this is our reducing agent. So ozonoids break down when they react with a reducing agent, and they will result in formation of final carbonyl fragments. So for example, this is our reducing agent, that's the dimethyl sulfide. It will form a fragment. And this fragment will further cleave down to produce our final carbonyl products. So these are our final product, and plus the uh, the remaining dimethyl sulfoxide, that's not the compound of our interest. So that's a reducing agent, so we don't need to worry about it. So this is the complete mechanism of ozonolysis of alkenes. Most alkenes are reduced quantitatively by molecular hydrogen in presence of a transition metal catalyst. Commonly used transition metal catalysts are platinum, palladium, ruthenium, and nickel. This process is known as catalytic reduction or catalytic hydrogenation. The addition of hydrogen in this process occurs with syn stereoselectivity, which means that hydrogens are added on the same side of the carbon-carbon double bond. Although the addition of hydrogen to any alkene is an exothermic process, so delta H is negative. But however, in absence of any catalyst, this process occurs painfully slow. So that's why we have to use a metal catalyst. Metal catalysts make this process go faster. The monosubstituted and disubstituted alkenes uh, show a good rate of reaction at room temperature under slightly elevated pressure, but tri-substituted and tetra-substituted alkenes, their rate of reaction is extremely low. So therefore, elevated temperature and elevated pressures are used in hydrogenation of tetra-substituted alkenes. The mechanism of catalytic hydrogenation of alkenes involve adsorption of both hydrogen uh, molecules and alkene molecules on the metal surface. When both the hydrogen gas and the alkenes are adsorbed close by, a transfer of hydrogen atom from the metal to alkene takes place, and thus uh, adding hydrogen to the carbon. Another transfer of hydrogen to the other carbon will result in formation of alkane, and it will leave the metal surface and clearing the path for another alkene to come and adsorb on the same metal surface. So hence metal act as a catalyst. It only provides surface for both hydrogen and alkenes where the transfer of hydrogens may take place. As you can see that in order for this transfer to take place, the hydrogen atoms are added on the same side. It's not possible for this hydrogen to leave the surface and then add on the opposite side. So that mechanism is not possible. So therefore, this reduction process gives alkanes with syn stereochemistry. So which means that the added hydrogens are present on the same side. Even though during the reduction of alkenes, the addition of hydrogen occurs with syn stereoselectivity, however, there is always some product which may appear to result from trans addition. So, for example, if we conduct the catalytic hydrogenation of this disubstituted cyclohexene, we find that 70 to 85% does have a cis uh, stereoselectivity, which is normal because it's a syn addition, so both the hydrogens should be on the same side, so which would result in a cis stereochemistry. However, a minor trans mixture is also observed. So this is strange. So if the addition occurs in syn stereoselectivity, how can uh, the product may be trans. Now, in order for this product to be trans, one hydrogen has to be below the carbon-carbon double bond and other one has to be above. So that looks like a anti stereoselectivity, but we said anti does not take place. Then how can we explain this one? The formation of this minor anti-substituted compound can be explained with this another reaction mechanism. Let me take an example. For example, if we uh, start with a cyclohexene and we conduct the hydrogenation, so we know that first cyclohexene will uh, adsorb on the metal catalyst surface. So this is our metal surface, and we have hydrogen also. So both of these alkene and hydrogen will adsorb, and when they adsorb, they will form a bond with the metal. So this would be hydrogen, and alkene will also form a bond with the metal, and then one of the hydrogen will be transferred from the metal surface to the alkene, and it would result in addition of hydrogen to one okay, one of the carbon atom. Now before the other hydrogen can add to the second, before this step take place, what happens is that in some cases a hydrogen from the neighboring carbon, that hydrogen gets transferred and it forms another alkene. So if, okay, let me redraw it. Okay, so at this point only one hydrogen has been added to our alkene. Now before the other hydrogen may add from the catalyst, the other hydrogen which is bonded to the catalyst, the hydrogen from the neighboring carbon atom, this one, that gets added. Now this addition is only possible on the opposite side of the sigma bond, and it would result in formation of a new alkene. I'm using different color for hydrogen to show that now it's a anti, and of course we're gonna get a new alkene, and this new alkene will go back to the metal surface again, and it will adsorb on the metal surface again, and the new alkene will be hydrolyzed normally. But once this new alkene gets hydrolyzed and it's released, it would appear as if the original alkene has a anti-stereoselectivity. And now we know that this anti-stereoselectivity is a result of rearrangement during the reaction mechanism. The heat of hydrogenation of an alkene is its heat of reaction with hydrogen to form an alkane. This table lists the heat of reactions for catalytic hydrogenation of several alkenes. Three main points can be derived from the information given in this table. The first point is that heat of the reaction is always negative. So that means the reaction is always exothermic. So reduction of alkene to an alkane is always exothermic. So there is net conversion of one pi bond and one sigma bond. So this is alkene and that's hydrogen. So one pi bond and one sigma bond break, but after that two sigma bonds are formed. So less energy is required to break a pi bond. So therefore we are spending less energy to break a bond, but we are getting more energy uh, generated when two sigma bonds are formed. So that's why the reaction is always exothermic. The second information we can obtain from this data is that delta H depends on the degree of substitution of the carbon atoms of the double bond. More substituted the alkene, for example, there is no substitution in ethene. That's the simplest alkene. It has a maximum negative delta H value. So maximum energy is generated in this reaction. In case of propene and 1-butene, we can see they have one substituent, so there's only one side is substituted. So their heat of reaction is slightly less than the ethene, but still considerably high. So more substitutions we get. So now it has 3 substitutions, and finally we have 4 substitutions. So we can see the heat of reaction is going down. Also, the third important factor is if we compare cis-2-butene and trans-2-butene, we will see that the heat of reaction is lower in case of trans, and in case of cis, the heat of reaction is higher. That is obviously due to the stability of cis and trans isomers. We know that trans alkenes are more stable. More stable means that they have less potential energy stored in them. So therefore, when they are converted into alkenes, less energy is generated. So with that, we finish all the reactions of alkenes. So these reactions mainly fall in two categories. One is the addition reaction, the other one is reduction and oxidation reactions.